Bismillahirrahmanirrahim. So this new topic is another functional group that we're going to look at. It's topic 19, and the name of the topic is carboxylic acids and its derivatives. Okay, so derivatives mean a compound that comes from carboxylic acid. Okay, so first things first, naming carboxylic acids, you know that they end with oic acid, okay? Depending on how many carbon atoms you have. Numbering, the carbon where your COOH is always number 1, okay? So that will always be carbon number 1, or we say that the COOH is always at the terminal because it's always at the end. Okay. When you have two carboxylic acid groups, COOH here, and another COOH, we call this a dioic acid. Okay, so that's why you get this name, dioic acid. Again, it depends on how many carbon atoms you have. Since you have two carbon atoms here, it's called ethane dioic acid. Okay. Talking about the physical properties of the carboxylic acid, for the solubility, okay, solubility in water. As you remember, in AS, I said that because water is polar, so usually a polar molecule will dissolve in a polar molecule, okay, because they have interaction, polar and polar, non-polar and non-polar. For compounds or molecules to be soluble in water, they need to form a hydrogen bonding or some sort of interaction. Usually it's hydrogen bonding, okay? Hydrogen bonding happens when you have a hydrogen attached to one of the three most electronegative elements, which is F, O, and N. And you can see that the hydrogen is attached to oxygen here. Okay, so this is where the hydrogen bonding is happening. The hydrogen that is attached to the carbon on this one, there is no hydrogen bonding there. Okay, so please take note that there is no hydrogen bonding happening there. If you want, you can label this dotted line as hydrogen bond. Same thing as this, okay, too thick. So the hydrogen bond happens on the slightly positive hydrogen and the slightly negative oxygen, okay? So I will not talk much about hydrogen bonding because that's already covered in your AS. Moving on, to explain the relative acidities of carboxylic acids, phenols, and alcohols. So in the previous topic, which is phenols, you've already talked about acidity, okay? Acidity of phenols. Acidity tends to depend on the stability of your anion, okay? Whether the anion is stable. If the anion is stable, that means more ions are formed, more ionization occur, therefore more acidic, okay? That's the first one in terms of stability of the anion. The second explanation is in terms of where the equilibrium lies. Does the equilibrium lie more onto the left or more onto the right? Okay, now the forward reaction is always ionization. That means if your equilibrium lies onto the right, okay, which is forward, then more ionization happens, more acidic. Okay, the third explanation is in terms of the strength of the OH bond. Okay, I will talk about this, and I find this as the simplest explanation among all the three. Okay, which one do you use? Well, if you understand all three, you should include all three in your answers, provided that they don't contradict with each other, okay? If you find it difficult to remember, you choose the easiest explanation that you can understand, okay? Right, so we want to compare the acidities of carboxylic acids, phenols, and alcohols. So among all these three compounds, you know that carboxylic acids is an acid, okay? However, it is a weak acid, right? So obviously the carboxylic acid is the most acidic among all these three, okay? And then from the previous topic, we learned that phenols are more acidic than alcohols, Okay, the reason is because of the delocalization. Okay, now before we look at the explanation, let's just have a look at the acidity of a carboxylic acid. Okay, now as mentioned, carboxylic acids are weak acids. Therefore, it still can release hydrogen ions in water or in solution. So when we write down the equation, which I think you need to copy down because in your notes it's empty, okay? So we take ethanoic acid as an example, CH3COOH. So there are two versions of the equation here. One is showing you the displayed formula, and the other one is just showing you the molecular formula, the structural formula. So when we release hydrogen ions in the solution, we are actually breaking this OH bond, okay? So when this OH bond is broken, you form a hydrogen ions and a carboxylate ion, or what we call, more specific is ethanoate ion, okay? So the general name for this is carboxylate. The anion of a carboxylic acid is called carboxylate ion, okay? Just like your phenols, when phenols dissociate into ions, phenols will form hydrogen ions and phenoxide. Okay, for alcohols, alcohols will dissociate into hydrogen ions and alkoxide. Okay, for example, when you dissociate ethanol, it forms ethoxide. Okay, when you dissociate phenols, it forms phenoxide. When you dissociate ethanoic acid, it forms ethanoate ion. Okay, when you dissolve or dissociate propanoic acid, it forms propanoate ion. Okay, they all end with ATE for carboxylic acid. So again, this is nothing new for you. When we write down the equation, please make sure that you've got your sign, positive and negative, because otherwise your equation wouldn't be balanced, okay? So if you look at this equation down here, on the left side, on the left side, you have a CH3COOH, which has no charge, neutral, okay? And then in the ions, you have a negative charge and a positive charge. So they cancel each other out, which is neutral. Now your equation is balanced, okay? Another thing about ionization or dissociation of acids, they are usually a reversible reaction, okay? Hence, you see a reversible arrow, okay? Only in strong acids that you see the ionization as a single arrow, because the equilibrium lies far to the right, okay? That's why HCl, we don't write it as a reversible arrow, okay? We write it, instead of a reversible arrow for HCl, the dissociation of HCl, we write it as a single arrow because we know that the equilibrium lies very, very, very much onto the right side, onto the ions. That's the definition of a strong acids, okay? But for weak acids, we write it as a reversible reaction because the equilibrium actually for weak acids lie on the left side, okay, more onto the left side. Right, I'm gonna erase that. Moving on, okay, before we move on, right? So explaining acidity, the first explanation is talking about the stability of this ethanoate ion, okay? Whether this ion is stable or not. If this ion is stable, that means it favors forward reaction, more acidic, more ionization, okay? If you want to label, maybe you can add forward is ionization or dissociation. Okay, the reverse is called association. And to know acidity, we want to look at the whether it goes forward, more dissociation, more acidic. Okay, the reverse is association. Okay, now let's have a look at the explanation. Okay, so you need to remember this ionization equation. Okay, so first explanation is the stability of this anion, whether this anion is stable or not. If it's stable, it will be formed. Okay, more of that ions will be formed. Secondly, you want to look at whether your equilibrium lies far onto the right side, which is ionization, or far onto the left side, which is dissociation. Okay, the third one is this, the strength of this OH bond. Okay, if this OH bond is weak, it is easy to break the OH bond. You release more H plus. Okay, if this OH bond is strong, that means it is not as easy to break the OH bond. You release less H plus. Okay, I hope you can relate more hydrogen ions with being more acidic, less hydrogen ions with being less acidic. Okay, right, let's have a look at the, no, not yet. So the strength of the weak acid is shown by the Ka value. Ka is the acid dissociation constant. If you remember Ka from topic 7, if I'm not mistaken, you have your products, which is CH3COO minus ions and your H plus ions over your acid CH3COOH. Okay, so if you have more ions, in which case big top, okay, that means you have more ions, your Ka will be big as well. This one is small. Okay, so a big Ka means more acidic because you have more ions, right? So the strength of the weak is shown by Ka value, where high Ka means the higher the acidity. Okay, pKa is the negative log of your Ka. So it has the opposite relationship to Ka. So big Ka, more acidic, that means your pKa is small, just like pH. If your pH is smaller, it is more acidic. For example, pH 1 is more acidic than pH 5. Okay, so the same thing for pKa as well. Okay, so pKa has the opposite property to Ka. If your Ka is big, your pKa would be small. Okay, again, before we talk about the explanation why carboxylic acids are more acidic than ethanols, we need to look at the structure and bonding of carboxylic acid. Okay, more specifically, it's the carboxylate anion. So this is the anion of your carboxylic acid. Okay, so if I draw your anion, normally we usually have, let's have an ethanoate ion. Okay, CH3 C double bond O minus. Okay, this is how you would usually draw your carboxylic ion. Okay, now you see this C double bond O. Okay, that is your pi bond. Okay, so your pi bond, if you still remember the bonding of an alkene, okay, your sigma bond flies flat on the plane. Okay, and then your, maybe I should draw this differently at an angle. So we have a CH3 COO minus. Okay, so now I'm going to draw the p orbitals that make up the pi bond. Okay, so the p orbital is perpendicular to the molecule. Okay, so this is the p orbitals that make up your pi bond. P orbitals that make pi bond. Okay, sorry, no space, so that's why I write it there. So the overlap of the p orbitals make the pi bond between the C double bond O. Okay, now there's another oxygen, the one with the negative charge. Okay, so I'll draw a different color. Actually, this oxygen, one of the orbital where the lone pair sits is perpendicular, or we say it overlaps with the pi bond. Okay, so what happens, because the pi bond and the p orbital of the oxygen, okay, are parallel or are all aligned together, so we have a delocalization of electrons. That means the pi bond is not only extended between the two p orbitals, the one in pink, but it is also extended towards the orange. I don't know how to draw this. I don't know if you can see it. But so basically you can see that the delocalization is like that. Okay, it's extended. Right, so let's have a look at the so what is the point of this extended or delocalized electrons? It stabilizes the ion. Okay, it makes the ion more stable. So the carboxylate anion is stabilized by the delocalization of electrons around the carboxylate ion COO minus. Okay, so let's have a read at the explanation. That's why you see this dotted line. If you're wondering why is that dotted line and why is the negative in the middle when you know that the negative belongs to the oxygen, okay? Because of the delocalization, they all now, these three, they share a same network. Okay, so that means the pi bond of the C double bond O is also extended to this oxygen, and the negative charge, which belongs to this bottom oxygen, is now being shared into this delocalized system. Everything is moving, everything is shared in this COO minus system. Okay, the R group has nothing to do with that. Okay, the alkyl group has nothing to do with that. So let's have a look at the explanation. So the pi electron cloud on C double bond O, okay, so that's the pink orbital here. The pi electron cloud on C double bond O has delocalized and spread out around the COO minus group. The delocalization makes the ion more stable and therefore more likely to form. Okay, because of this delocalization, the negative charge that belonged to the oxygen is now spread out. Okay, we're not saying that the carboxylate ion is no longer negative. It is still negative, but instead of writing down this negative charge on the oxygen, we move it to the middle to show that this negative charge is now being spread out between the COO part of the molecule. Okay, so because the negative charge is spread out, therefore it is less likely to attract H plus. Okay, why? If we look at this equation, this negative charge, see, we draw the negative charge on the oxygen, but actually because of delocalization, the negative charge should be in the middle. Okay, now this negative charge is now less concentrated, or we say weak, because it has been spread out to COO. Okay, so because this negative charge is not as concentrated, it does not attract the H plus much. Okay, when it doesn't attract the H plus much, the reverse doesn't happen a lot. I mean, it can still happen, but not a lot. Okay, so if the reverse reaction doesn't happen, then that means you're favoring the forward reaction, which means you're favoring more ionization. Okay, so that's the second explanation, which I think is a little bit more difficult or more complicated to explain. Okay, the first explanation is easy by saying that the ethanoate ion or the carboxylate ion is stable because of the delocalization between the pi bond of the C double bond O and the oxygen. because of this delocalization as well, the negative charge is being spread out into spread out over the COO minus. Okay. The last explanation, explanation number 3, is this. Okay, this one is not looking at the carboxylic ion, but it is looking at the carboxylic acid. Okay, so if I number them, explanation number 1, explanation number 2, and then this one is explanation number 3. Okay, the OH bond is weakened by the carbonyl group C double bond O. H plus is hence easily lost. Okay, so explanation number 3, you have to look at the carboxylic acid, not the carboxylate ion. Okay, so these two explanation looking at ions, okay, which is carboxylate, not enough space. But explanation number 3 is looking at carboxylic acid, because we want to talk about the OH bond. Okay, so this brings me to the next slide. Now, why do we talk about the carboxylic acid? This is explanation number 3. Okay, this is frankly my favorite explanation because I find it easy to understand. Okay, now oxygen, FO and N, oxygen is one of the well, I know you have 2 oxygen here, okay, but oxygen is one of the most electronegative elements. Electronegative means the element or the atom has a tendency to pull electrons. Okay, so this oxygen is a highly electronegative, which means it pulls oxygen towards itself. Okay, I'm sorry, it pulls electrons toward itself. Okay, so that means this oxygen that I've labeled in pink, okay, I'll remove this. This oxygen in pink is pulling some of the electrons from the C double bond O bond. Okay, so some of the electrons go to oxygen. Now this has a chain effect. Okay, the electrons in the CO bond is also being pulled to the pink oxygen, as well as the electrons in the OH bond. So this arrow, this red arrow, is showing you that the electrons in these bonds are being pulled towards the oxygen. Now it's not completely pulling all the electrons, but just the electron density is shifted. Okay, now the one that I'm interested in is the OH bond, because that's where the bond is broken to release H plus. Okay, right, now because I am taking away electrons from the OH bond, this OH bond becomes weaker. Okay, so when you take electron density away from a bond, the bond becomes weaker. Right, now because the bond is now weaker, it is easier to break the OH bond. When the OH bond is weak, easier to break the OH bond, then you release H plus easily. When you have more H plus, it is more acidic. Okay, I find this the easiest to understand, but you have to remember this red arrow showing you that the electrons or the electron density are being drawn or attracted towards this pink oxygen. Okay, I have one student asking, what about this oxygen? It is also electronegative. Yes, this oxygen is electronegative. That's why it's pulling the electrons from the OH bond. However, because of the chain effect, okay, this pink oxygen is pulling all the electron bonds, electron density from the C double bond O, C single bond O, O single bond H. Okay, now when you remove electrons away from the bond, where you're not really removing it completely, it's just that you draw it out of the bond becomes weaker. Okay, Right. I hope that it is something that you can understand. Okay, so there are three explanations. As you can see, explanation 1 and 2 focuses on the carboxylate ion. Explanation number 3 focuses on this the strength of the OH bond, which I think is the easiest to explain. Okay, so that means when you arrange these three functional groups in terms of acidity, carboxylic acid is the most acidic and alcohol is the least acidic. So now to explain, carboxylic acid has the most stable anion among these three. Okay, so remember carboxylic acid, I'm going to write R as an alkyl group. Okay, this is an alkyl group. C double bond O, O minus. Phenol has an anion of that. Alcohol, I'm just going to make up that. Okay, now why is carboxylic acid the most stable? Again, for the same reason, because of the delocalization in the COO part of the anion. Okay, so the negative charge is being distributed around the COO part of the molecule. Okay, that explains why carboxylic acid is more acidic than phenol. Okay, if you want to explain why phenol is more acidic than alcohol, then you also talk about the delocalization of phenol. Okay, this negative charge on the oxygen is being spread out or being delocalized into the ring. So every time you see a delocalization, that means it's stable. Okay, alcohol doesn't have any stabilization. Okay, if anything, alcohol has an alkyl group which has an electron donating effect. Alkyl group, okay, which is electron donating effect. Okay, so what this alkyl group does is that it adds negativity to an already negative charge. Okay, so this is very, very unstable. The anion of your alcohol, or what we call an alkoxide, is very, very unstable because you have the alkyl group, which is electron donating group, donating more electronegativity to someone who is already negative. Okay, you don't want that. You want to remove the negativity from the person. That's what delocalization is doing. Okay, here the negative charge is being spread out. So instead of focusing it or putting it on oxygen alone, the negative charge is being spread out into COO minus. Okay, now I draw it like this, but strictly speaking, if you look at the previous part, the negative charge is actually here, being spread out in the middle. Okay, likewise for phenol, this negative charge is being delocalized into the ring. Okay, the reason for this is because of the pi orbital in the ring overlaps with the orbital on the oxygen, like that. Okay, they overlap. Same thing like your carboxylate ion. In a C double bond O, there is a pi bond, like that. I'm just going to draw it like that. And then one of the orbitals of the oxygen where the lone pair is sitting happens to be parallel to the pi bond of the C double bond O. That's why delocalization can happen. Okay, they overlap extension. Okay, so please this one is strength of carboxylic acids. How many? Okay, I will talk about this tomorrow. I will not continue since we only have 8 minutes left. Basically, the strength of the carboxylic acid. Now, in this first part, we are comparing carboxylic acid with the other functional groups. Okay, why carboxylic acid is more acidic than phenol and alcohol. Okay, but the one that we're going to cover tomorrow is comparing the carboxylic acids. Okay, they're all carboxylic acids. We know that they are all weak acids, but why is some carboxylic acid more acidic than the other? Okay, so that's what we're going to look at. So that means we're going to look at the electron donating and electron withdrawing group. You already know that an alkyl group is electron donating. Okay, so if you look at this carboxylic acid group, this is a methanoic acid, ethanoic acid, and propanoic acid. Okay, so if you look at the pKa, remember, the smaller the pKa, the more acidic. So we're going to explain why methanoic acid is the most acidic among all these three. Okay, so we cannot talk about the delocalization because all these three acids have COOH. They all have the delocalization. So the one that we're going to focus on is the alkyl group that is attached to the COOH. Okay, the COOH is not the determining factor here. It is the alkyl group. Okay, so that's for tomorrow. And then another example is when you have a chlorine attached to your carboxylic acid group. So if you look at this, here you have 3 chlorine attached to that carbon of your carboxylic acid. Here we have 2 chlorine, and here we have 1 chlorine. And if we look at the pKa values, it tells you that the 3 chlorine group that is attached to that carbon of your COOH is the most acidic. So tomorrow we're going to explain why. Again, we cannot talk about the COOH because they all have the COOH, the same COOH. They have the same sort of delocalization. They have the same stability, but it all depends on the chlorine, the number of chlorine that you put in that molecule. Okay, chlorine has an electron withdrawing effect. Here is another example where you have a fluorine, chlorine, bromine, and iodine in a carboxylic acid. Okay, and they have very different acidity as well. Okay, so we'll talk about that tomorrow. Before we go, do you have any questions? Let me just erase this first. Question to ask? Anything that is not clear on these slides? No?
So basically,